Welcome back, students, to Unit 4a, Ionic Bonds. Today we'll be focusing on the properties of ionic bonds. In this course, we have already talked about metallic bonds. However, metallic bonds are not part of the Virginia SOL, and so while I will have questions in this unit's test on metallic bonds, there are actually only two types of bonds that the SOL requires you know. Ionic bonds, which we are talking about in this unit, and covalent bonds, which we'll talk about in the next unit. Ionic bonds are formed from ions, things that have a true positive and true negative charge, because the cation transfers electrons to the anion, forming those positive and negative charges. Ionic bonds traditionally are formed between metals and nonmetals. A good rule of thumb is that if you have two elements in a bond that are on opposite sides of the periodic table, that is an ionic bond. Covalent bonds are formed exclusively between nonmetals in which they share electrons, and we will focus in the next couple weeks about covalent compounds. You've actually already seen some covalent compounds in this course when we talked about water. Water is a covalent compound. Hydrogen and oxygen are both nonmetals, and they're held together by sharing electrons. Your polyatomic ions are also covalent compounds. Sulfur shares electrons with 4 oxygens and has an extra 2 electrons, which gives it a -2 oxidation state. That covalent molecule can pair up with metals such as sodium to neutralize that charge. Sodium sulfate, therefore, is both ionic. You have a metal and nonmetals, but it's also covalent in the fact that you have a covalent bond between the sulfur and oxygens. Ionic bonds are held together by the attraction of positive for negative. This is known as an electrostatic force, and it obeys Coulomb's law that the force of attraction is proportional to the charges divided by the distance between them. Ions with large charges experience a stronger attractions. Ions that are very small experience a large attraction. The stronger the attraction between your ions, the higher the melting point, the amount of energy it takes to separate these ions from one another. So with that being said, you're able to answer your first 4 note quiz questions. Pause the video and answer questions 1 through 4. If you wanted to separate the ions in an ionic compound, if you wanted to melt it, you would have to overcome its lattice energy, the amount of energy that's holding it in its lattice-like structure. And as this is an attraction of something positive for something truly negative, this usually requires a vast amount of energy. You can actually predict lattice energies of salts relative to one another if you look at Coulomb's law, where the force of attraction is proportional to the charges divided by the distance between them. So in this example here, we could explain why sodium chloride has a much higher lattice energy than sodium iodide. They are all +1s and -1s. So the charge aspect here is not really what we're looking at. Instead, what matters most is the fact that chlorine comes down to the fact that chlorine is in the 3rd energy level. So chlorine has 3 shells around it, while iodine is in the 5th energy level, having 5 shells. So iodine is way larger. Since iodine is a much larger ion, that means that for iodine, the force of attraction, for iodide, the force of attraction is proportional to the charges divided by a very large distance, while for chlorine, the force of attraction is proportional to the charges divided by a very small distance. So the force of attraction for chloride, sodium chloride, is much greater than the force of attraction for sodium iodide. You can also use Coulomb's law to explain why magnesium sulfide would have a greater lattice energy or a higher melting point than sodium chloride. Magnesium sulfide are both in the same period as sodium and chloride. However, their distances, their radii, are approximately the same. However, magnesium is a +2 oxidative state and sulfide is a -2 oxidative state. So a +2 and a -2 would cause this numerator to be much greater than sodium chloride's +1 and -1. So the force of attraction for magnesium sulfide is greater than the force of attraction for sodium chloride, so magnesium sulfide would have a higher melting point, a higher boiling point, greater lattice energy. Coulomb's law is a great way to explain or predict these values. However, you don't need to actually worry that much about those lattice energies because you can actually separate ions from one another fairly easy by putting salts, ionic bonds, into water. Water has a partially negative side, the oxygen, and a partially positive side, the hydrogens. Since it has these partial charges, water is actually able to pull the cations from the anions through a process known as hydration, separating them from one another. The oxygen end of water, which is a little bit negative, will surround the cations and pull it apart. The hydrogen end of water, which is a little bit positive, will surround the anions and pull them apart. Since cations are made out of metals, these cations can actually be used to close a circuit. In class, we talked about how they form electrolytes. Electrolytes are ions that in solution are mobile and able to close a circuit. Being free and mobile allows them to close a circuit between two electrodes to carry a current. If you place a salt in water and it produces lots of ions, so for example sodium chloride, sodium and chloride don't have as strong an attraction for one another as they do for the water, so every single sodium chloride becomes sodium ions and chloride ions, producing massive amounts of ions in solution and therefore are a strong conductor of electricity. So we call these strong electrolytes. They can conduct electricity very well. However, if your salt has a stronger attraction for itself than it does for the water, it might produce very few ions in solution. An example of this is acetic acid. Acetic acid, only a handful of these hydrogen ions actually come out in solution, so it is a very weak conductor of electricity, so we call it a weak electrolyte. But if you place a compound in solution and none of them form electrolytes, this is known as a non-electrolyte. Non-electrolytes are traditionally covalent compounds, so things like sugar. Sugar is a non-electrolyte. It does not dissociate in solution, it does not separate, because these covalent bonds are not attracted to the water. They cannot come apart. So covalent compounds are traditionally non-electrolytes. They do not form any mobile ions and therefore they cannot close a circuit and conduct electricity. So you are actually able to represent this by writing what's known as a dissociation equation. In a dissociation equation, we show the cations separating from the anions. So for example, hydrocyanuric acid separates into hydrogen ions, the cations, and cyanide ions, the anions. You separate your cations from your anions. The easiest way to think of this is to separate your metals from your nonmetals, because metals traditionally form your cations. Muric chloride, you would separate your mercury from your chloride ions. Since we started with 2 chlorides, we would need to have 2 chlorides when we finish. However, separating the metals from the nonmetals is not exactly what's going on. Again, it's separating the cations from the anions. In ammonium hydroxide, there are no metals. However, ammonium is the only positive ion you were supposed to memorize. Ammonium is a cation, so it separates from its anion, hydroxide. So, if you look in your packet at example 8, we cover dissociation equations. Sodium acetate is going to dissociate when we put it in water. So we start with solid sodium acetate and put it in water, and it undergoes dissociation, where the cation, sodium, is going to leave the anion, acetate. These are ions, so they retain their charges in solution, and they're in solution. So we denote this by writing that they are aqueous, AQ, at the end of each one, to say they're in water. Ammonium phosphite would separate its cation, ammonium, which is your only positive ion, from its phosphite. Phosphite has an oxidative state of -3, and ammonium has an oxidative state of +1. Since I started with 3 phosphites, I have to end with 3 phosphites. You could also tackle it from this idea of charge. 3 plus 1s are canceled out by 3 minuses. Again, these will be in solution, so you say they are aqueous after each one, and those are your dissociation equations. With that, you're able to answer your last 4 note quiz questions, as well as do page 14. On page 14, parts A and B on both the top and the bottom are where I suggest you start, because they give you half the equation and you just have to figure out what's missing. So in this first example, they give you that chloride is produced. So what's left over? The calcium is the only thing that's missing, so you simply plug in calcium. Remember that you can use the oxidation states to figure out the oxidation states of transition metals, like number 4, chromium. Chromium is what's missing. You have 2 chromiums and they have to cancel out the charge of this oxide. You have 3 oxides, so that's a -6. So 2 somethings -6 have to equal 0. That something must be a +3. And with that, we are now done with Unit 4A. Next time in class, we will be taking our Unit 4A test with 25 multiple choice questions. You will have a free response, and since we have not had a free response practice, we haven't had a quiz in this unit, I will tell you what the free response is. For the first part of the free response, I will give you some element like sulfur, and I will say sulfur forms an ion. What ion does it form? And you've got to say sulfur has a -2 oxidative state, becoming sulfide. Then I'll say sulfur reacts with the polyatomic ion ammonium to make ammonium sulfide. What is the formula for ammonium sulfide? And you would have to remember that ammonium is your only positive cation. Ammonium's a +1, so it would take 2 ammoniums to neutralize a sulfide. Then I would say ammonium sulfide is highly soluble. when it's placed in solution, write the dissociation equation for ammonium sulfide. You'd have to do what we did in this video, where ammonium sulfide, the cation, is separated from the anion. I might ask you about its hydration, how the oxygen end of water is attracted to the ammonium, and how the hydrogen end of water is attracted to the sulfide. But beyond that, that will be your free response for your quiz. And I'll see you in Unit 4B, covalent bonds.